This hand just picked up a coffee cup without moving a single muscle, without speaking a word, using only a thought. Not years from now, not in a laboratory far away. Right now, in 2025. Welcome to the moment mind control became reality. His name is Brad Smith. 3 years ago, he could move his whole body, walk, hug his kids, type a message. Today, he can move his eyes, nothing else. ALS, amyotrophic lateral sclerosis, stole everything but his mind. For years, he communicated like this, one letter at a time. It took him 45 minutes to write a single paragraph, to tell his family he loved them. And then, in early 2025, surgeons opened his skull and placed something impossible inside. This, smaller than a coin, 64 threads, thinner than human hair, 1,024 electrodes, each one listening to individual neurons in his motor cortex, the part of his brain that still knows how to move, even if his body can't. 3 weeks after surgery, they turned it on and asked him to do something simple. Think about moving your right hand. Nothing happened. His hand didn't move. It couldn't. The connection to his muscles was severed years ago. But on the screen, something extraordinary. 1,000 neurons firing in perfect coordination. A symphony of intention with nowhere to go. We can read it. We can translate it. And here's where it gets incredible. They connected his brain not to his body, but to this. For the first time in 3 years, Brad moved something. But how? How do you translate thought into motion? And why did it take us until 2025 to figure this out? Your brain speaks in electricity. Every thought, every intention, every memory, it's all electrical signals cascading through 86 billion neurons. When you decide to pick up a cup, here's what happens. Your prefrontal cortex makes the decision. Your motor cortex plans the movement. Neurons fire in precise sequences, hundreds, thousands of them, coordinating trajectory, force, timing. Those signals race down your spinal cord at 120 meters per second. They trigger muscles to contract. Your hand moves. But for Brad, the signal stops here. The neurons fire, the intention exists, but the bridge is broken. So the question becomes, can we listen to those neurons directly and translate their electrical language into something a computer understands? In 2025, 3 companies are racing to solve this puzzle, and they're doing it in completely different ways. Synchron, backed by Bill Gates and Jeff Bezos, chose the path of least resistance, literally. Their device, the Stentrode, doesn't require open brain surgery. Instead, it enters through an incision in your neck, travels up through blood vessels, and unfurls inside a vein sitting just above your motor cortex. It's like putting a microphone outside a stadium instead of inside. You hear the crowd, but you miss individual voices. Lower resolution, safer surgery. Paradromics went the opposite direction. Their Connexus interface has 1,681 electrodes, the highest bandwidth in the field. Matt Angle, their CEO, describes it like this. We're putting microphones inside the stadium, close enough to hear individual conversations, not just the roar, the words. In May 2025, they completed their first human implant. 20 minutes, proof of concept, removed the same day. They're targeting communication speeds of 130 words per minute, near-natural speech. And then there's Neuralink. 1,024 electrodes on 64 threads, implanted by a robot precise enough to avoid blood vessels. The R1 robot threads these electrodes into your quartz like a sewing machine. Automatic, microsurgical, trying to minimize damage. 3 philosophies. Synchron, minimal invasion, lower bandwidth. Paradromics, maximum data, focused on healthcare. Neuralink, consumer-grade ambitions, optimizing for scale. But all 3 face the same fundamental challenge. Your brain doesn't like foreign objects. Within weeks of implantation, your immune system surrounds the electrodes with scar tissue, a process called gliosis. The signal gets quieter, fuzzier. Early brain-computer interfaces failed after months. The body won the war of attrition. When Nolan Arbaugh became Neuralink's first patient in January 2024, he was playing video games, moving cursors, controlling his computer with thought alone. And then, weeks later, some of the threads retracted, pulled back from the tissue. Signal quality dropped. Week 5 after Nolan's implant, signal quality dropping, cursor accuracy declining. The threads were retracting, pulling away from the tissue they needed to read. Nolan felt it happening. The cursor that had been responsive started lagging. The chess moves that had been instant became delayed. The device that had given him independence was slipping away. Nolan thought, here we go again. Another promising thing that doesn't last. He tried to stay hopeful, but it was hard. For a moment, it looked like the same old story. Another promising technology dying in the brain's hostile environment. The team had a choice: recommend surgical revision, replace the implant, reset the clock, risk complications, or find another way. They chose another way. Instead of trying to fix the hardware position, they taught the software to listen harder, to extract more information from fewer, weaker signals, to predict Nolan's intentions even when the data was noisy. They trained the algorithms not just on what his neurons were doing, but on what they were trying to do. Context, history, intent. 2 weeks later, thread position still suboptimal. Signal strength still degraded. But cursor accuracy back to 100%. The implant didn't heal. The software got smarter. That was the moment everyone realized this isn't just hardware implanted in brains. It's a human-machine learning system. Both sides adapting, both sides improving. Co-evolution in real time. For every success you're seeing, there were decades of failures. Monkeys controlling robotic arms in the 90s. Human trials in the 2000s where signals degraded in months. Technologies that worked in the lab but died in the body. This moment, this breakthrough, is built on a graveyard of impossible attempts. By November 2025, 12 people worldwide have brain-computer interfaces. Not in distant futures, not in science fiction, alive. Right now, using them. Nolan, paralyzed from a diving accident at 20, now plays chess, browses the web, uses his phone, all with thought alone. Alex, who received his implant in July 2024, is learning to use computer-aided design software, creating three-dimensional objects, engineering with his mind. And Brad, remember Brad? He now controls a periscope webcam. He can look around his room, watch his family, take photos. After years of being trapped in a fixed gaze, he can see. Brad. For the last few years, I've had ideas and thoughts I couldn't share, because it took too much time to type them out. The first time Brad tried to type his son's name with the BCI, it took him 9 minutes. The cursor wandered, his attention drifted. The algorithm hadn't learned his patterns yet. It was reading his neurons, but it didn't understand his language. His son waited, watching the screen, watching his father, watching a technology that promised freedom, but felt like another prison. Brad closed his eyes, breathed, tried again. And then, something clicked. Not in the machine, in Brad. He stopped trying to control the cursor. He stopped thinking about the technology. He just thought about where he wanted to go. And it went. His son's name appeared on screen. Complete, clear, correct. His son smiled. Brad cried. 3 weeks later, Brad was typing 30 words per minute, faster than he could with his old eye-tracking system. Fast enough to tell jokes, fast enough to argue, fast enough to be himself again. Brad. Now, I can already communicate faster than before. We're still working on ways to get even faster. In April 2025, Brad narrated and edited an entire YouTube video, using only brain signals. Brad. I want the world to see ALS not merely as a tragic endpoint, but as an opportunity for profound growth and innovation that highlights human resilience. This is what technology can do when it remembers it's supposed to serve human dignity. So how does it actually work? How do you turn thought into motion? Step 1. Record. The implant listens to about 200 to 300 neurons simultaneously, a tiny fraction of the billions in your brain, but enough. When Brad thinks about moving his hand, specific neurons fire in specific patterns. These create voltage spikes, tiny electrical events lasting milliseconds. Step 2. Decode. Machine learning algorithms trained on Brad's brain learn what patterns mean what intentions. This pattern means move right. This one means click. This one means select. Step 3. Translate. The decoded intention becomes a digital command, an API call, a mouse movement, a robotic servo instruction. Step 4. Execute. The device moves. The thought becomes action. All of this happens in less than 1/10 of a second, fast enough that it feels natural, like moving your own body. But here's the extraordinary part. The better Brad gets at using it, the better the algorithms get at reading him. Human and machine, co-learning, co-adapting. In his first week, Brad could move a cursor. By month 3, he was editing videos. The technology isn't just reading his brain, it's learning to speak his language. Which raises a question no one's quite ready to answer. When does a tool stop being external and start being part of you? But not everyone shares the optimism. Dr. Grace Kao, neuroscientist at MIT, frames the concern. We've seen this before. Deep brain stimulation for Parkinson's works. Cochlear implants for hearing work. But dozens of other neural interfaces failed. The brain is more complex than any technology we've built. She's not wrong to be cautious. In the 1990s, researchers trained monkeys to control robotic arms. We thought human trials were 5 years away. That was 30 years ago. Second Sight Medical developed the Argus retinal implant. It gave limited vision to blind patients, low resolution, grainy, but functional. Some called it miraculous. In 2022, the company went bankrupt. 350 patients were left with devices implanted in their eyes. No support, no software updates, no repairs. Hardware in their bodies, no one to maintain it. So when someone says brain implants will change everything, it's fair to ask, what happens when the company fails? So what's different this time? 3 things. 1. Machine learning. Early BCI used static decoding. If the signal changed, they failed. Modern BCI adapt continuously, learning your brain as your brain learns them. Nolan's thread retraction would have ended early experiments. Today, the software compensated. 2. Wireless power and data. Early implants required wires through the skull. Infection risks, mechanical failure. Modern BCI are fully implanted. Wireless charging, wireless data. Nothing penetrates the skin. 3. Economic momentum. This isn't one company, it's an industry. If Neuralink fails, Synchron continues. If Synchron fails, Paradromics continues. The knowledge compounds. The progress is distributed. No single point of failure. Will every promise be delivered? Probably not. Will some patients face complications? Almost certainly. Will this technology fail some people? Yes. But will it help many people? It already has. And that's enough to keep going. Because restoring lost function is just the beginning. Neuralink's Blind Sight project aims to restore vision, not by fixing damaged eyes, but by sending visual information directly to the brain. Early prototypes see like old Atari graphics, pixelated, crude, but functional. And in theory, they could exceed natural vision. Infrared, ultraviolet, zoom, enhancement. Speech restoration is accelerating, using AI to decode the neural patterns of intended speech, before vocal cords, before breath. In studies outside Neuralink, patients with ALS have communicated through synthesized speech at rates approaching normal conversation. Not typing words, thinking them. And then there's the closed loop. Most current BC is send signals one way, brain to device. But what if the device could send signals back? Touch, pressure, temperature. The robotic hand doesn't just move, it feels. This is bidirectional neural integration, the line between biology and technology dissolving. Every transformative technology brings a question. Should we? We've been here before. Television would rot our brains. The internet would isolate us. Smartphones would destroy attention. And yet, here we are. Using those tools to learn, create, connect. But brain-computer interfaces feel different. Because they don't just augment what we do, they might augment who we are. Restoring Brad's ability to communicate, that's medicine. Giving someone superhuman memory or enhanced cognition or direct brain-to-brain communication, that's something else. Who gets access? If these devices cost hundreds of thousands of dollars, do they widen the inequality gap? Who owns the data? If your thoughts can be decoded, who controls that information? What happens if the company goes bankrupt? If the device needs an upgrade you can't afford? If the part of you that's digital becomes obsolete? These aren't hypothetical. They're happening now. Every BCI trial requires FDA oversight, institutional review boards, informed consent that explains risks we're still discovering. This technology is being built not just by engineers, but by ethicists, patients, regulators, society. By the end of 2025, Neuralink plans 20 to 30 more implants, expanding to Canada, the UK, Germany, the UAE. Synchron has implanted 10 patients. Paradromics is launching full clinical trials. Precision neuroscience is refining less invasive approaches. The neurotechnology market is projected to reach $400 billion, not in some distant future, by 2035. Beyond paralysis, Parkinson's disease, epilepsy, treatment-resistant depression, PTSD, and beyond medicine, enhanced memory, accelerated learning, communication without language barriers. But maybe the most important thing isn't the technology, it's what it represents. For decades, we told people like Brad, "This is your life now, adapt." Today, we're saying something different. The world will adapt to you. In 2025, the line between mind and machine didn't just blur, it dissolved. 12 people are living proof that thought, pure intention, can command the physical world. Not through muscles, not through speech, through the electrical language of neurons translated into digital action. Brad can now control a webcam, play games, edit videos, communicate at near natural speed. All through 1,024 electrodes thinner than hair, listening to a few hundred neurons out of the billions in his brain. A few hundred neurons. That's all it took to give him back his voice, his agency, his connection to the world. And that tells us something profound. For millions of years, we've been limited by biology. Our senses could only detect a narrow slice of reality. Our muscles could only exert limited force. Our minds could only communicate through sound and gesture. And then we started building tools. Tools that extended our reach, amplified our strength, preserved our thoughts. Brain-computer interfaces are the next step in that ancient pattern. Not replacing what makes us human, enhancing it. Not diminishing biology, transcending its limits. For all of human history, the barrier between mind and world was absolute. Thought stayed locked inside. Action required flesh, bone, muscle. Not anymore. By the end of 2025, 20 to 30 more implants. By 2030, hundreds, maybe thousands. By 2040, who knows? Vision for the blind, speech for the voiceless, motion for the paralyzed. And beyond that, possibilities we haven't imagined yet. The brain-computer revolution isn't coming. It's here. 12 pioneers are living it right now. Brad, this is what happens when we refuse to accept impossible as an answer. This is Cosmic Canvas, where we witness the impossible becoming real. Until next time, stay curious, stay hopeful, and remember, Your thoughts are more powerful than you know.